and we will start off with Mihai Horanyi at University of Colorado. As a reminder, I will give everyone a 5-minute warning when you're almost out of time, and we will have time for more discussion at the end of the session if we don't get all the questions answered during the talks themselves. So take it away.
Thank you. I hope you can hear me and
yes, we
see
can
the
hear
slide.
you and see you. Yes.
Thank you. So this talk is about an instrument, the Lunar Meteoroid Monitor. The next slide, please. So typically we discuss meteoroids in two groups, showers and the sporadic background. And the only difference is that the sporadic background is particles that forgot their parent bodies. As long as dust particles orbit is similar to the parent body, they will show up as streams and meteor showers. Maybe some of you had a chance to go out, last week and look for the Perseids. When they hit, they come and hit the Earth and deliver cosmic material, cosmic dust, about or on the order of 100 tons per day. If you just scale it to the moon, that's about 5 tons per day of incoming dust that is continuously reworking or gardening the lunar surface. Next slide, please. Of course, at Earth, because we have an atmosphere, these incoming dust particles, most of them will not reach the surface, but we can observe them as shooting stars visually, or you could also use radar meteor stations to monitor the speed, direction. But the precise knowledge of how much dust, what's the size and speed distribution after many decades of ground-based observation still escapes us. The next slide, please. Of course, the moon does not have an atmosphere. So the same flux that reaches the Earth, that would directly reach the surface of the moon and generates secondary particles, ejecta particles. The vast majority of them would have speeds below escape speed. So they follow kind of ballistic orbits. They jump up and eventually fall back down to the surface. The next slide. We had an incredible mission not so long ago, 2013, 2014, the LODI mission. That's the spacecraft on the left. So the top right is the trajectories. It started out at 200 kilometers above the surface, then dropped down to, between 100 and 50 and so on. And it is an impact ionization dust detector. So on the bottom right, a dust particle comes in, hits a target, generates a puff of plasma that is separated by an electric field and record the electrons and the ion signals, and that would tell us the size of the dust particle. The typical speeds of a dust with respect to the lunar surface is much, much smaller than the spacecraft. The spacecraft was going 1.7 kilometers per second, as opposed to the dust particles. Most of them will be recorded at their turning point. So the relative motion with respect to the moon is just a few or tens of meters per second. The next slide. That's it's all the data. It's a function of time. The daily average impact rate of particles bigger than 0.3 micron. That was the threshold for individual detection of single impacts. Once per minute, even as high as 200 kilometers above the surface, the little 100 square centimeter effective dust detector was hit once per minute. If you were looking for bigger particles, like 0.7 micron or so in radii, then you had to wait 10 minutes between impacts. Another curious information on this plot is during the northern turrets, the Geminids, the Quadrantis, and so forth, these are the meteor showers where you see the dust cloud. The dust cloud engulfing the entire moon was enhanced. These are much higher speed, short duration, several days worth of events, when the impact rate was enhanced during these periods. The next slide, please. So other than the periods of enhanced activities, you can then paint a picture of the average dust cloud above the lunar surface. On the left is data. There is the black segments is either that we couldn't take data because the instrument would not work if it was pointing directly at the sun, or the spacecraft never visited. But then, of course, with a bit of mathematics, you could try to expand that and make a nice smooth fit on the right. That is our expectation of the average lunar dust cloud, the dust density in units of 10 to the minus 3 cubic meters. And on these plots, the sun is to the left, the Earth-Moon system is moving towards the top of the slide. Next slide, please. So these are the special periods, so the Northern Taurids, the Geminids. For a couple of days, the impact rate was certainly enhanced, and we can recognize the meteor showers through their effect of the production of the ejecta cloud. Next slide. So why do you care? I mean, throughout this session, you're worried about the surface, and other parts of this meeting is about volatiles and so forth. Because, as far as dust goes, there is no permanently shadowed region. Regardless where you are, maybe up towards the poles, when there is a hope that volatiles will accumulate and we could go to these regions and use them for ISRU, find resources, volatiles, possibly water. As far as dust impacts go, these regions are not protected. So dust impacts in general, of course, could release volatiles. They could migrate nevertheless, but then they remain exposed to impacts. They can deliver dust and bury them, or through ejecta production, remove them. And with all honesty, we really don't have a good model. What is the net production or loss, transport, and input to the permanently shadowed region, and how does dust impacts affect what is there to be worked with for ISRU, for example? The next one. So these issues that we need to learn the dust impact environment of the moon were recognized very early on. And this was the Lunar Ejecta and Meteoroid experiment left behind Apollo 17 and worked for 30 lunations or so. Maybe at some other meetings we could discuss what did or did not show up on the LEAM measurements. But dust itself made the LEAM measurements complicated because this instrument overheated during the day. So this transition from day to night, night to day, even though it is frequently used as proof of electrostatic transport and so forth, you should remember to take that as a grain of salt, because these measurements are difficult and the interpretation of the LEAM data is somewhat of an open issue. The next slide. Even today, of course, we carry these unknown problems forward, and this is the Artemis Science Definition Report, things that we need to learn. Goal 6K and Goal 6.7. This is what's the micrometeoroid bombardment and so forth. And we need to monitor meteorites, micrometeorites, and so forth to successfully maintain human habitats and work long periods of time safely on the lunar surface. The next slide. So what is the expectation that we think we know? And that is in situ measurements of dust impacts by instruments carried on spacecraft, like Galileo and Cassini, and even earlier ones like Pioneer 8 and 9 and so forth. And of course, also like the long duration exposure facility that was up for several years, and then panels were brought back and we looked at the craters that were left behind. That's on the left. It's a function of particle size or mass. That's the flux. And then those little yellow lines indicate that if you could measure particles as small as 3 microns impacting particles, then you would have a dozen or a couple dozen, maybe 20 impacts per week that you could record on the lunar surface. On the right, that's our best understanding based on dynamical models of what happens with the speed. What is the speed distribution? The blue is at Earth, where gravitational focusing is dominant. And of course, you see the escape velocity from the Earth as a cutoff minimum velocity. The moon is not so good about gravitational focusing, so this greenish area is what is expected as the speed distribution at the surface of the moon of the impacting particles.
5 minutes.
All right, thank you. The next slide. So to answer, back to the LEAM original Apollo 17 issues or the Artemis issues, you would like to monitor what's coming to the surface, what's the size and the speed distribution. And this is, that's the standard NASA way to formulate what you need to do. The science traceability matrix as an example. The next one, please. So it turns out that the fluxes are relatively modest, so you need a large surface area, and the type of instruments that you could use would, employ thin plastic films. PVDF, polyvinylidene fluoride films, have been used as dust detectors. They are permanently polarized, and when the particle excavates a crater, they generate an electrical signal. You could do 2 of these layers, one below the other, so the penetrating particles then will impact the second layer, and you could measure the time of flight and get the charge that they generate, and the speed that you measure allows you to figure out the mass and the speed of the incoming particles. The next slide, please. So it has to be a little bit thoughtful because you have to penetrate the top film, and given the size distribution, the plot on the left, those straight lines on the log-log scale going across, like the green one. If you were to have a 6 micron and a 3 micron, a 6 micron PVDF film, and for thermal reason, it would have a silica oxide coating and so forth. What are the particles that would penetrate? And turns out that most 3 micron particles would actually go through. There is a catch. As they go through the 3 micron film, they lose some speed. So the speed that you measure is not the incoming speed, but we have some modeling and lab results to tell you the slowdown as a function of mass and speed of the incoming. So the one on the right would tell you how to make a correction from the speed measurement between the films to the speed measurements that would be the speed of interest, the incoming velocity. The next slide. This is a possible implementation. Of course, a large surface area, like half a square meter, you cannot launch on a spacecraft. It's way too big. So you could think of a deployable structure. This would be on a rover, for example. The 24-inch semicircle deployed version is on the left. You could see the 2 films, 6 micron, a thin film on the top, and the thick film, 28 micron on the bottom. And on the right, it's in a stored configuration that would allow you to launch and put it on the rover and then deploy it on the lunar surface. So my last slide, I believe, is next, please. As a summary, these are the things you will have to worry about when you design an instrument like this. You have to have a deployable structure because you cannot, put on a small spacecraft or a bigger spacecraft, a large surface area dust instrument. If there are arguments that it would be really good to survive the lunar night. So clearly, in that case, low power electronics is a key. You have to have very low power consumption, so you would survive the lunar night, as opposed to the difficulty of surviving the lunar day when things get very hot and you have to have good thermal control, that these films remain permanently polarized and they can be used even when the temperature goes and swings from minus 170 to plus 120 from night to day. But in principle, you could envision that an instrument like this could be deployed as part of a lunar environmental monitoring stations, and arguments are around that we could build rovers that would have an expected lifetime well over 2 years, safely surviving the temperature swings from day and night. Thank you.
Okay, perfect timing. Thank you.